So, we have been discussing about electrical braking on DC shunt or separately excited motor. In DC dynamic braking, what is done is armature only disconnected, it is running as a motor initially, then only armature is disconnected from the supply. Armature is only disconnected from the supply with this switch and connected across the resistance. Then eventually I know what will be the FET. The direction of the armature current then will reverse, armature current will flow this way, electromagnetic torque developed will be opposite to the earlier electromagnetic torque. So, it is like you are braking the motor. You must apply an opposing torque in the direction opposite to the direction of rotation for executing braking. And I told you how to calculate the braking torque at t equal to 0 plus. In case of dynamic DC dynamic braking, highest braking torque will be at t equal to 0 plus, then speed eventually falls, back EMF decreases. The braking torque is in itself is a function of time, it gradually collapses to 0. But in this case flux is maintained. Okay. An improvement, if you want to bring the machine much faster than the DC dynamic braking, then what you do? You make an arrangement, right hand side arrangement is almost similar to that, except that along with this R you connect a source, say same supply voltage, you bring it here, and the polarity of this source should be properly with respect to this E B, it must be properly connected, so that E B and V together acts in the same direction. So, at t equal to 0 plus, here the current at t equal to 0 plus will be much higher than simply k phi n naught by R A plus R, plus V supply will aid, larger braking torque will be developed. Because there are machines with large inertia, you want to bring it to stop quickly, such a method should be then adopted. And in this case also field you have to maintain. If you also disconnect the field, okay, it will not work, because flux will collapse, EB will collapse. Of course, got the point. Phi into IA is the torque. So, the another method is there, that is called regenerative braking. Okay. Here the idea is interesting. In previous cases, what we did, that initial that kinetic energy stored is dissipated in R, is not? Ultimately, eventually it is dissipated in R. So, it is like this. In regenerative braking, what happens is this, that braking will take place, but really not for bringing the machine to come to a stop. Let me tell you one thing. For example, you see that there is a track here, okay, and you have a loco here, and the motor drives this wheel so that it moves in this direction, and here is the supply lines, and the negative is connected to the rails, and the power is collected by say pantograph or whatever it is supply. So, here is a DC motor, you imagine it is driving this, and it is moving smoothly on a smooth railway track. Okay. Now, suppose so it is running as a motor, giving moving this vehicle or loco from left to right. Okay. A DC motor is driving the wheel. Now, so in normal case, when it is on the flat track, it will run as a motor, fine. Now, you imagine that this track is has got a slope like this. Okay. This is the supply lines V, and your vehicle comes here. There is a downhill in the track, and your this thing, this is the where, this will be the scenario when it negotiates this downhill, and it will still moving in this direction. Now, when it was moving on the flat track, then the electromagnetic torque developed by the motor is also equal to the opposing load torque present on the machine, and let us imagine it is a shunt motor. But the moment it comes to this portion of the track, which is having a ramp down here, then gravity mg whatever it is, its weight, there is additional force will come which will accelerate the rotor apart from the electromagnetic torque, whatever is acting, but there appears an torque force or torque because of the component of the gravity present. For example, forget about any supply connected, if you just keep a vehicle like this, it will just accelerate in this direction. Forget about your supply is not there, a vehicle put on wheels, you put it here, it will on its own come down, it is not mechanical thing. Now, in such a situation what happens, suppose when it was in position 1, this is suppose position 2, vehicle has reached. Initially, we know that the machine is having a finite no load speed, is not? This is speed, and speed varies like this. So, when it was here, it was drawing an armature current IA1 shunt motor. This is the speed versus armature current characteristics. It was running at this speed and running as a motor. It was drawing an armature current. I am not showing the motor armature field here, just to give you the idea. Okay, it was drawing an armature current here, and it was running at this speed, delivering mechanical power to move this vehicle or traction. Now, when it comes to position 2, what will happen is this: the speed of the rotor of the machines which are coupled to this wheel, that will go on increasing, accelerating, is not? Speed will go up, that is operating point will move here, got the point, it will move here, speed will increase. A time will come when speed, this is the no load speed, how much is its value? V by k phi is equal to n naught, we have seen that. Okay, I will draw it slightly nicely. So I am now telling its speed increases beyond n naught, because of some external, as if sort of prime mover is present. What was the circuit here? When it was on the flat track, it was like this: R A, back EMF and your supply. V, and it was drawing a current I A. And let us imagine separately excited machine or whatever it is, shunt motor also no problem, field is always connected like this. This is position 1 and not, this is not I A, it was drawing this current and your I A was this motoring mode. Electromagnetic torque in this direction, direction of rotation was in this direction, this is position 1. Now, in position 2, what will be the scenario? Scenario will be, this is the field, this is the armature, supply voltage is still V here, and here is R A, and here is your back EMF in series, those things remaining intact. But this back EMF was proportional to K phi into whatever was the speed here N1, like that. That was the back EMF, and it was less than supply voltage, that is why current was flowing in this one, V minus E B by R A. Now, I have a situation where in this zone maybe the speed has gone up to higher value, such that this back EMF E B 2, the speed has become greater than N naught, it is K phi N naught or N, anyway N1. So, E B 2, it has become such that speed has become K phi N 2, speed is higher at this point N 2, and which is greater than V. Then what will happen? Field current will remain in the same direction, nothing like that, V by R F, but your armature current will reverse, is it? Because this voltage minus V divided by R A is the new armature current, E B 2 is greater than supply voltage. It may so happen, because it was accelerating like this and your I A 2 reverses. And as I told you, the moment I A 2 reverses, it was moving in this direction, electromagnetic torque developed by the machine must reverse, because I A 2 has become like this. So, operating point has become, so it is minus I A 2, and therefore, an opposing torque comes in, and your machine will then experience opposite torque, opposite with respect to N. Therefore, braking takes place. Okay. But it will not bring the machine to stop. What it will do? It will find another operating point doing like this, but it will do one very important thing. It will not make this vehicle uncontrolled. I mean, like a free fall, mg sin theta will accelerate it down. It soon will find a final velocity higher than the initial no load velocity, no doubt, but it will stabilize the thing. So, regenerative braking will put free acceleration not possible. I mean, will not make this free acceleration possible. It will, but nonetheless it is braking. Got the point. So, this is called regenerative braking. Why regenerative? Because in this case one interesting thing happens, that this current, this power will be fed back to the supply. IA2 will come and IA2 minus IF whatever it is, here if you apply KCL, that will flow to the positive terminal of the supply. So, power will be fed back to the supply. So, kinetic energy whatever will be lost or gained, there is no loss of power, no external resistance connected. Therefore, regenerative braking means that the machine speed, when it becomes greater than the no load speed of the machine, a natural reversal of current in the armature will take place and it will produce torque in a direction opposite to the direction of rotation of the machine, and thereby some braking torque will be produced. And once again I am telling, it will not bring the machine to a stop. So, regenerative braking are very interesting method of temporary braking, which will not allow the rotor to accelerate freely just like that, and at the same time the power will be fed back to the supply. Clear? So, there are interesting problems on this, you can try solving. Therefore, these are the three methods which I have not gone much detail into it for obvious reasons, but you get the idea what it will be. Just use very basic principles of motor generators, see the direction of the torque develop, and in this case also field flux is held fixed here, nothing like that. So, there are interesting problems in the book of Parker Smith's, we will point them out in our handouts, you try to solve them. Okay. Now, today I will give you, after discussing about the electrical basics of electrical brakings, I will tell you about another kind of motors which are called series motor. Series motor, DC series motor. Okay. Now, there is a kind of motor where this was the armature, is not? In our basic structure is same, these are the poles. This is A1, A2 armature. Now, this field coil will be very few number of turns, but thicker wire. Okay. First, let us see the construction. This is the field coil. On each pole, it will be connected like this. So, these are called, and these two will be connected in series. These are connected inside the machine, and these two terminals are marked as AC1 and AC2. So, fewer turns, thick wires. In case of shunt machine, there were large number of turns, thin wires. Okay. And these two are as usual the armature terminals. So, this machine in the simplified diagram can be drawn like this. This is your armature, two terminals A1, A2, and there is the two terminals AC1 and AC2. And while connecting this machine, this armature is connected in series with the field, and here supply will be connected to run it as a motor. Got the point? So, in this case there is no shunt field coil, there is only one coil with very few turns, because everything comes in series with the armature, must have very low resistance. Okay? And here I will connect the supply, that is the thing. So, I can make a motor like this and I will connect it to the supply. So, but because of this, will all the derivations that we have done, back EMF, torque will change? No, not at all. Here what is important is this is the flux per pole, this is the armature current, these two will decide everything. Flux per pole, whether it is created by a series field coil or shunt field coil, armature does not care about that. If it is running, it will develop a generated voltage K phi n, that remains. It will be able to produce an electromagnetic torque that is proportional to K phi into I A, that is all. So far as the basic equations are concerned, flux per pole is now merely created by some coil which is conditioned like that, their connections, etc. And also note that in this case the armature and field current, they are same, this is series field. Armature and field current are same. So, no point in distinguishing between IA and IF, they almost become same. Okay. So, I will be connecting here. So, there will be series field resistance RAC, and here is the motor armature. Flux per pole will be created as usual, flux per pole, and this armature circuit will then look like an RA with some back EMF, and here is some RAC in the electrical equivalent circuit I am telling, and there may be brush drop as usual. This is the supply, and this is the current drawn by the machine, and this is your back EMF. Achha, let us try to understand it from the very beginning. Suppose you have a switch here, this I will tell verbally. By this time I hope you understand what I am telling. Suppose machine was at rest, okay, and I have closed the switch. At t equal to 0 plus, how much will be the current drawn? Machine was at rest, there was no back EMF. Back EMF is K phi n. In this case, flux per pole is also proportional to I, that I know. It is equal to some k dashed into I into n, because phi is proportional to n. At t equal to 0 plus, when you close the switch, machine has not started yet rotating. At t equal to 0 plus, the equivalent circuit will be RA, RAC, and your supply. So, current drawn at I 0 plus will be equal to V divided by R A plus R A C, that is all. This much will be the current. But machine has not started yet, so no back EMF is there. So, equivalent circuit at t equal to 0 plus is just like this. So, a finite current which may be very large because armature resistance are small, RAC is also small, will be drawn in from the supply. And will there be electromagnetic torque developed? Yes, because electromagnetic torque is equal to some kT into phi into IA, which in this case will be some kT other constant I square, that is all. So, electromagnetic torque will be developed and machine will accelerate, it is there. Now, as machine accelerates, that is n increases, EB increases, back EMF will appear now after machine starts accelerating. So, this is the circuit I have to refer to get the current. So, IA will be V minus IA into RA plus RAC divided by V minus EB, is not V minus EB. Let me write EB divided by RA plus RAC. This will be the current as machine picks up speed. What is EB? EB is equal to some K into phi, neglecting saturation, field current is same as the current drawn I. So, K I N. This will be the current, this is also I, and EB depends on I, this is to be noted. As machine picks up speed, EB increases, but I also decreases, is not. Now, the question is, what will be the final steady operating point? Machine speed will go on increasing and it will try to settle down steadily at some point, where the load torque will be equal to the electromagnetic torque developed by the machine. Suppose there is opposing torque present. So, T L should be equal to T, and that will be equal to K T into I square. Electromagnetic torque is this one. Suppose my machine finally settles down to this. So, at the final steady state operating point, it will draw some armature current. And what is your I? I will be at that time is equal to B minus that steady state current, that is EB is equal to K phi, I mean K I B minus B by RA plus RAC. This will be these two equations then, because flux is proportional to I. Neglect saturation, neglect saturation. So, this is the thing. Now, there are 2-3 observations I must tell at this point. Imagine a shunt motor. Okay. In case of shunt motor, and suppose in shunt motor the torque is shunt motor. These are interesting points you must note, that is, one is electromagnetic torque in shunt motor is K I f into I a, is not electromagnetic torque developed. I f is V by R f, it is no way connected with I a. What is the value of at the point of shunt motor at the point of starting? The point of starting, what is the armature current? Armature current will be V by R a only, and I f is finite V by R f. So, armature current is large V by R a into I f gives you the starting torque. So, T starting torque will be this much. Come to series motor. During series motor, the starting current is k T into I square, but what is the starting current? I starting in series motor is how much? V by R a plus R a c. R a plus R a c is of the same order of R a. Therefore, armature current is very large. In both the cases they are comparable. V by R a it was there, it is V by R a plus R a c. But the point I want to make it is that in case of series motor, the starting torque is proportional to I square. Therefore, the magnitude of the starting torque is manifold higher than the starting torque of a shunt motor. Very large starting torque you can get. How I am telling that? Because of the fact armature resistance and series field resistance are comparable. So, I starting in case of series motor back EMF is not there, V by R a plus R a c, and in case of shunt motor it will be V by R a starting current. Torque is proportional to I f into I a. I f is finite, which is small in case of shunt motor. So, a large quantity I a into a small number here. In case of series motor, T starting is equal to K proportional to I square, and this I is same as this I starting. Therefore, a series motor can produce a very large starting torque, unlike a shunt motor, okay, which is there are uses of this particular thing. For example, I will today only tell this point and then next class we will continue. You suppose you imagine that you have to crush some nuts, hard nuts you have to crush with a, say what it is called, crusher something. At the time of starting, they are hard, the nuts are. So, you will be requiring very large torque at that time. Okay. But after the nuts break, becomes fine particles, then you do not require large torque. We will see that there are loads which require very large starting torque. For example, in traction, a heavily loaded say wagon, it is to be started. At the time when you want to start that locomotive, which is fully loaded, that means the opposing torque is very large, already present on the shaft. But to make it start, you must develop enough starting torque. For shunt motor, if you use it may not reach that one, because IF by design is small. IA may be large, V by RA, but IF is small, finite. But if you use a series motor, then large starting torque can be created, V by RA plus RAC, torque is proportional to I square, and it is indeed necessary when you want to start that locomotive, which is heavily loaded, fully loaded at the time of starting. But as it accelerates and attains some finite speed, do you require that much of torque? Certainly not. Torque required to overcome the inertia is gone now. Therefore, you will be requiring less amount of torque to run the locomotive at some constant speed. We will come to this point in a much more detailed way in our next lecture, but only thing I want to tell you that no matter whether it is a shunt and series motor, do not forget those two basic equations, back EMF equations, V minus some IA RA drop. In case of series motor, it is IA into RA plus RAC minus maybe brush drop, and that is equal to back EMF. So, there may be different situations when the applied voltage is this, torque is this, what is the current drawn, etc. So, I will write down in each cases the back EMF equation and what else? The torque equation, T1 equal to TL1 for steady operations and T2 equal to TL2. And we will also see another interesting thing in the next class, that a series motor should not be started with any mechanical load present on the shaft. That is also another interesting thing. In case of shunt motor, even if there is no opposing torque or load torque present at the time of starting, you have a finite speed, machine will go to that speed and will run. But a series motor, without any mechanical opposing torque, load torque present, if you want to start the motor, we will see there is no finite speed, machine is racing to a very large value, creating problems. Those are interesting things we will discuss in my next class. Thank you.